Okay, so we started out today by reminding ourselves of something from last time, and that is that normal is a smart force, which means it will adjust based on other forces acting on the object, as well as tension. And so I just wanted to make sure you have that in your notes as we started. And then today we're going to talk about how you solve problems involving either accelerating or not accelerating objects by analyzing what forces are acting on them, and then solving for either the unknown force or the acceleration or the mass, whatever this is we're looking for. And I want you to have these in your notes. These are guidelines that will help in no matter what kind of problem you're solving. If it's involving forces and Newton's second law, then these the rule and these guidelines will get you a long way. So first of all, I call it rule number one, and it's not technically a rule. I mean, you can break it, but you're going to make more silly mistakes algebraically and otherwise if you don't follow it. Or you're going to make the problem a lot harder than it has to be. So write it down for now, and then you'll see as we work problems what it means. But rule one says that if there's an acceleration, make it along an axis and positive if possible. We've seen this even from projectiles, right? I insisted on making down positive just because that's the direction of the acceleration. I was kind of setting the stage for where we're going here. Now, can you work a problem with the acceleration being negative? Well, sure. You just have to remember that it's negative every time you plug it into your calculator. So that seems silly to me. What if you don't know? Right? It says if possible because sometimes you don't know the direction of the acceleration, and so you guess. And if you end up with a positive answer, you guessed right. If you end up with a negative answer, don't worry. You don't have to redo anything. You just guessed wrong, and so you just flip it, and it's going in the other direction from which you guessed it would be. So make it positive if possible, but sometimes you don't know. All right, and then you have these three steps. First step is always draw a free body diagram. All the forces acting on the object, and be sure and designate the positive directions and resolve any vectors that are in more than one direction. Now, again, you'll see this in action here in a second, but basically, if it's not along an x or y axis, if it's a vector that's in both directions, then you have to resolve it. Again, we saw this with projectile motion. We had an angled launch. One of the first things you had to do was break it apart into components because the accelerations were different in the two different directions. And if we follow rule one, we're going to have only an acceleration in one direction. And so we need to make sure we have everything in their components. All right, so step one is the harder step. It's the most critical step. But the good news is if you do that right, then you really have a hard time screwing it up on steps 2 and 3. Step 2 is to what I call write an F-net statement. And that's just a sum of, it's writing a statement of what all the forces are acting on the object. And then the third step, because F-net equals ma, we're going to substitute mass times acceleration, or ma, for the expression for the net force. All right, so again, get those in your notes, but then let's see what that actually looks like. So here's an example of a problem. You say that a cable lifts a 14-kilogram box with a constant acceleration of 0.43 meters per second squared up, and the question is, what is the tension in the cable? Now, you're tempted to do a lot of things at first, but trust me, follow the process, do these 3 steps, and you can do easy problems like this, but you'll also be able to do much more involved ones. And you won't fall into silly pitfalls that students have when they're trying to do even easy ones like this. All right, so step 1, draw the free body diagram. What forces are acting on this box? Well, there's mg down and tension up. So I'm going to draw those. I don't have any forces that are in both horizontal and vertical directions, so there's nothing to resolve, but I do want to go ahead and clearly indicate the positive direction. The problem has told me that it's going to accelerate up, so I'm going to choose up as my positive direction. Is that all the forces acting on this box? Yes, and so step 1 is complete. Now, why I say steps 2 and 3 are so easy is because they completely just follow from step 1. From this free body diagram, I can look at it and say, hey, what are all the forces acting? Well, there's only one direction for this particular problem, the vertical direction. So I can say the sum of all forces in the vertical direction are, well, I see I have one force pointing in the positive direction, what I called up, and so I call tension a positive force. So I write positive T for tension. And then I have one force that's in what I've called the negative direction, mg. So I write minus mg. Are there any other forces in the diagram? No. Am I done with step 2? Yes. Again, it comes straight off of that free body diagram. All right. Then step 3 is substitute MA. So in place of F net on the left side, I'm going to write MA. So MA in the y direction equals T minus mg. Again, straight substitution. Now the question asked me about the tension, so I can solve for the tension. I rewrite the equation as T equals MA in the y direction plus mg. Then I substitute everything that's given, the 14 kilograms for the mass, the 0.43 for the acceleration in the y direction, and 10 for g. And I get an answer of 146 newtons up. And that's actually the right answer. By the way, quick note here. Don't ever, ever, ever let anybody tell you that g is negative 10. G is not negative 10. On the surface of planet Earth, g has a magnitude of 10 meters per second squared, or 9.81 if you want to be a little more specific. But 10 meters per second squared down, right, towards the center of the planet, that's not inherently negative. It depends on which direction you choose as positive. And so don't ever say that g is negative 10. It's 10 meters per second squared towards the center of the planet or down. If that happens to be negative in your particular reference system, that's fine, but that's not g being negative. That's g being down in your frame of reference. And the reason I point that out is because I've had students doing problems like this ask me, well, isn't g negative 10? So wouldn't it be minus 14 times negative 10? And the answer is no. We already took into account the fact that it's down by drawing it pointing down. And because we designated this as up as a positive direction, by saying negative or minus mg, we already took care of the direction. So g is a vector, and so that negative is just a direction indicator. So there's nothing inherently negative about g. It's just g down, which sometimes makes it end up with a negative value. All right. So let's ramp it up just a little bit. This time we have a horizontal force of 124 newtons acting to the right on a 16 kilogram block on a horizontal frictionless surface. How fast is the block going after 2.1 seconds if the block was initially at rest? So what am I going to do first? I'm going to draw a free body diagram. What forces are acting? Well, of course, there's mg down and normal up. And then there's this new force that they've told me about that's acting to the right. I don't know anything about it. I just know that it's pointing to the right. I could have drawn it originating on the right side if it's a pulling force. I chose to make it originate on the left side because I'm saying it's a pushing force, but that's not given in the problem and it doesn't matter. All that matters is that it's pointing to the right. And I've labeled it force applied. This is kind of a generic label we give forces when there's not anything really specific given about what the origin is. We just say something outside of it is applying this force. So that's what that's there for. And that's it, right? Those are the only forces acting. Now, again, looking at this picture, I can tell that the forces are unbalanced, and therefore there must be an acceleration, and the acceleration must be to the right because of that unbalanced force. The question is, what is that acceleration so that I can figure out how fast the block's going? So have I finished step 1? Well, almost. I don't have anybody in both horizontal and vertical directions. All of the vectors are in just one of those two dimensions. So I don't have anything to resolve, but I do need to clearly indicate the positive directions. Following rule 1, I'm going to make right positive, and then up or down, it doesn't really matter because there's no acceleration in the y direction. All right, so now that I have step 1 complete, I can move on to step 2. Straight from the free body diagram, I'm going to start with F net in the y direction there's a normal force in the up direction, so I call that positive, and there's an mg force in the negative direction, so n minus mg. In the x direction, the net force in the x direction is just the applied force. So that's the only force there, so that makes that easy. Substituting ma into the y direction, ma in the y direction equals n minus mg. And because it's only moving horizontally, there's no vertical motion. It's not moving vertically, much less accelerating, so I know the acceleration is 0, and that just tells me that n and mg are balanced in this case. Now, that doesn't surprise me, right? I know that if it's not accelerating up or down, then normal and mg are balanced, but this is the mathematical proof. Now, if I turn my attention to the x direction, I can substitute ma in the x direction equals the applied force. I'm interested in acceleration. That's what's going to get me closer to the speed. And so I solve for acceleration, which is the force applied over the mass, which is 124 over 16, which tells me 7.75 meters per second squared to the right. So now it's just a matter of going back to what we learned like week 3. I have a constant uniform kinematics equation, uniformly accelerating kinematics equation that says that the speed now is the initial speed plus the acceleration times the time. They told me it starts at rest, so v initial is 0, and acceleration now is 7.75, time is 2.1. I plug those in, and I get a final speed of 16.3 meters per second. Now, I could have asked for the velocity of the ball, the block, in which case it would have been 16.3 meters per second to the right, but I only asked how fast, so it doesn't matter if you indicate the direction or not. All right. All right, so now we're going to really ramp it up, literally. We have this frictionless ramp that's at a 20-degree angle. We're going to have this block slide on it, and it's a frictionless surface, so it's going to accelerate down the incline. That's pretty straightforward, pretty much expected. And then I pointed out, what do you expect the acceleration to be? Do you expect it to be greater than, less than, or equal to 10 meters per second squared? Well, obviously, if you let it slide down the incline, that's not going to accelerate just as fast as dropping it. So just a kind of a heads up, as we're working this, if I end up with a number that's greater than 10, I know I did something wrong. So let's just always ask yourself if your answer is reasonable as you're working a problem. All right, so what do? Well, step 1 is to draw the forces, right? Draw the free body diagram. So there's only 2 forces acting on this object. There's mg towards the center of the planet, and normal, which is acting perpendicular to the surface by its definition. Again, looking at that, I can tell that those are not balanced this time, right? N and mg are not equal and opposite, so it's going to accelerate. It's going to slide down the incline. But now the question is, where do I go from here? And well, this is where, oh, by the way, I just pointed out that oftentimes on the College Board exams, they will give you like a dot or a block like this and ask you to draw the forces acting on it. If that free body diagram is separate by itself, and they say draw a free body diagram or a force diagram on this image, be careful to only draw the forces on that image. And they've gotten good now. Recently, in the last couple of years, they've gotten to where they specify do not draw components. If you need to draw components, do that elsewhere. So if it's a scored free body diagram, it should look like what's on the bottom left here, and not what's going to end up looking like in the middle of the screen. So just keep that in mind. All right, so if I go to finish out step 1, I need positive directions, and I need to figure out who to resolve into components. So let me just ask you something. If I keep a traditional coordinate system like this, notice where the acceleration is. The acceleration is down and to the right. That means I will have an acceleration in the x direction and in the y direction. And I don't know about you, but that sounds like a lot more work to me. So that's why I'm not doing that. Rule 1 says if there's an acceleration, make it along an axis. So in this case, the acceleration is definitely not along your traditional x and y axes. So I'm going to come up with a better coordinate system. I'm going to make the x and y axes tilted like this, to where x is along the incline and y then is perpendicular to the incline. The advantage of that is now, notice, the acceleration is only in the x direction, not in the y direction. And so when I go to assign positive directions, I say down the incline is positive x, and in the direction of normal is positive y. I care about the red one. I care about the horizontal direction because there's an acceleration. I don't care about the vertical. I could have made opposite of normal, positive, but I was just going with kind of what most people feel comes naturally. All right, so now I know who I want to resolve. mg is now both in the horizontal and vertical directions. And so I need to resolve mg into its components. And so I've redrawn it up here in the top right, just so you get a better feel for, we have more room to show what we're doing. if mg is both in the y direction and the x direction, it has these two components. I'm going to call or actually first let's talk about this angle. What is this angle? That angle is 20 degrees. How do I know that? Well, there's two ways I can prove it. One is this orange triangle I've drawn. With this orange triangle, you can see that this angle here has to be 70 degrees, right? And if that angle is 70 degrees, then that means this angle has to be 20. So that's one way to prove it. The other way is more of a kind of a conceptual way to think about it. How much did we tilt the horizontal axis by? Well, 20 degrees, right? We tilted it 20 degrees because of the incline. So how much will mg be deflected away from the y-axis? Well, of course, the same, 20 degrees. So those are the two ways that I can prove that that angle drawn in the top right-hand corner is 20 degrees. So now I turn to trig to get the components. I know that if I call that vertical component y, then I'm going to use cosine because y is adjacent to the 20 degree angle. And I can say that cosine 20 degrees is y over mg. Therefore, y equals mg times cosine 20. And I'm just going to relabel on my middle image there, my working free body diagram, that the vertical component is mg cosine 20. I can do the same approach for the horizontal component, only I'm going to use sine because it's opposite the 20 degree angle. And so sine of 20 degrees equals x over mg. Therefore, x equals mg times sine of 20 degrees. So I've redrawn mg as two components, a horizontal and vertical component, and they are mg cosine 20 for the vertical and mg sine 20 for the horizontal, or the x direction. And here's what I wanted to point out, right? Notice what's in the middle has the components. That's my working free body diagram. That's what I'm going to use to get the answers. But if they have a free body diagram that they've asked me to draw separately that they're going to score, I don't want it to look like that. I want it to look like this free body diagram to the bottom left, which doesn't show the components, only shows the individual forces. All right, so I'm going to remove that so that I have room now to work on step 2, which is writing my F-net statements. Again, it comes straight from the free body diagram. If you look in the x direction, there's only one force acting in the x direction. So the sum of all forces in the x direction is mg sine 20. That's it. If I turn my attention to the y direction, I have two forces in the y direction. Since I've called up positive, I'm going to say that the sum of all forces in the y direction equals n minus mg cosine 20. Now notice, neither one of these equals mg. I've broken down mg into its components, and so the F-net statements are going to have the components of mg in them, not mg itself. So don't get slipped up there. All right. Step 3, substitute ma. In the y direction, ma equals n minus mg cosine 20 degrees. The acceleration in the y direction is 0. Remember, that's why we rotated the coordinate system, so that the acceleration would only be in the x direction. It's not in the y direction at all. And so 0 equals n minus mg cosine 20. Therefore, the normal force is not equal to mg this time. It's equal to just the vertical component of mg, or mg cosine 20. Now, in the spirit of full disclosure, we don't need that. Honestly, until we have friction, we don't really necessarily need to know the normal force, but we're practicing it so that we get good at the process. Turning my attention to the x direction, F net in the x direction equals ma in the x direction, which equals mg sine 20. I can divide by m, and that means that a equals g times sine 20. Now I know everything. I know g is 10 and sine 20 is 0.34. So the acceleration is 3.4 meters per second squared down the incline. And that's the answer to what the acceleration is. All right. And then we did one more example, a little more complicated, but still, again, the exact same process. This time, it's a 60-degree angle. It's still frictionless. I have a 4-kilogram block, and I'm pulling up in the direction up the incline with a 50-Newton tension force. Right? I've got a string attached to the block, and I'm pulling upward with a 50-Newton force. And again, the question is just, what is the acceleration? Well, same process. I'm going to define the coordinate system and draw the free body diagram. Again, I want the acceleration to be along an axis, so I tilt my coordinate system to where it lines up with the inclined plane, which means I have normal in the positive vertical direction, I have tension in the negative horizontal direction, and mg is both vertical and horizontal, so I need to resolve it into its components. Again, the exact same trigonometry I did in the previous problem. I end up with mg cosine 60 for the vertical component. I end up with mg sine 60 for the horizontal component. And then I write the F-net statement in the y direction. The sum of all forces in the y direction are, n is the one in the positive direction, mg cosine 60 is in the negative direction, so it just equals n minus mg cosine 60. Because the acceleration is 0, then ma equals 0, n equals mg cosine 60. Right? It's starting to sound really familiar, right? It's kind of going to be like that for the majority of the problems, but again, follow the process in case they throw me a curveball. All right, so n is mg cosine 60. Again, since there's no friction, honestly, I don't really care about that, but we're just showing this process. I turn my attention to the x direction. Notice this time x is different. The sum of all forces in the x direction this time is not just mg sine 60. There's also a tension force in the negative direction, in the opposite direction. Now, by the way, I should have said this. I assumed the acceleration was down the incline. I didn't know for sure. I wasn't positive, and so I just picked one. If I end up with a positive answer, then I assumed right. If I end up with a negative answer, then that will tell me that I assumed wrong. But I'm just going to start moving through and see what happens. So F-net in the x direction equals mg sine 60 degrees minus t. Step 3, substitute ma. ma in the x direction equals mg sine 60 degrees minus t. Now, most common error right here is if you're going to solve for a, you need to divide by m. But dividing by m is not just canceling these two m's. Does every term have an m in it? The answer is no. ma has an m in it, so when you divide by m, you get a. mg sine 60 has an m in it, so when you divide by m, you get g sine 60 degrees. But you can't just say then minus t, because you divided ma and mg sine 60 by m, but you didn't divide t by m. So you have to do t divided by m. Right? That's what's happening. When you cancel an m, you're dividing by m. But you get to cancel it if there's no, if everybody has an m. If not every term has an m, then you can't just cross them out. You have to literally divide everything by m. So don't forget that. That's a common mistake, to lose that t over m there in a problem like this. All right, but if I remember to divide by m, now when I substitute the known values and solve for a, I get 3.84 meters per second squared, and I got a negative answer. Do I panic? No, I just said, hey, I assumed down the incline was positive, so if I end up with a negative answer, that just means it's up the incline. So I'm going to report the final answer as 3.84 meters per second squared up the incline, which tells me a couple of things. One, tells me it's slowing down, right? Because the problem started off telling me that the block was moving down the incline, so if the acceleration is up the incline, acceleration and velocity are in opposite directions, so it's slowing down. But then also, it tells me that the tension force was greater than that horizontal component of the gravitational force that was trying to speed it up down the incline. And that's why it's slowing down. And if I let it keep doing this, it's eventually going to switch directions and start going up the incline as well. All right. One more thing about that. Whatever you do, though, don't say negative 3.84 meters per second squared up the incline, right? Negative up would be down. So either... the best answer is to use the words. Don't use the positive directions because we made up the positive directions. So the best answer is 3.84 meters per second squared up the incline. But just be careful. If you're going to use a negative, don't use a negative and a direction that will end up canceling each other and give the exact opposite answer of what you meant to. All right, so you've got plenty of practice on MyPCA for Newton's second law problems. Those are due, I believe it's this weekend, in preparation for the exam next week. And then notice the one thing we haven't done is friction. And so you have a virtual lab that you have to finish before class next time. That notice on MyPCA, it says do start a class. So make sure you finish that virtual lab before next class. All right, thanks.